A pulse crosses the star's light like a metronome set too fast for geology. The dip is narrow, repeatable, and arrives in hours, not days. The starlight returns, the curve smooths, and then the cycle repeats, clockwork carved into photons. From the timing of that cadence and the depth of that shadow, one statement emerges with the weight of an axiom. The world that casts it is compact, searing, and impossibly heavy for its size. This should be impossible. Spectra say the star is ordinary, a quiet furnace with predictable lines and a stable temperament. Yet its reflex motion, tiny shifts in the wavelengths, pushed and pulled by the orbiting mass, betrays a gravity too large for the world's silhouette. The silhouette is small. The pull is not. Gravity demands something denser than rock, denser than any basalt or peridotite can pack at those pressures. The data point sits off the familiar curve where rocky planets live. It does not wander. It lodges there, like a rivet driven into a steel beam. Something hidden was waiting in the dark. The orbit hugs the star so closely that heat on the dayside climbs to furnace levels, a temperature at which silicates soften, metals glow, and any volatile gas flees. The planet circles fast enough that tides have locked its face, pinning one hemisphere to perpetual day and the other to a night lit only by the star's reflected fire. In such proximity, mantles blister. Crusts fail. Atmospheres abrade into the stellar wind. A rock would expand if it carried even a thin envelope, its radius puffed beyond the compact disk we measure. Yet the measured radius stays small, held tight like a coil under compression. The inference grows sharper. What orbits there is not a typical rock. It is a near solid core. The language of the data is austere. A fractional dip of starlight, a radial wobble, a slight glow in the infrared when the dayside turns toward us and then vanishes at eclipse. But taken together, these sparse signatures outline a body with bulk density beyond the reach of silicate planets. In mass, radius, space, a map where worlds find their families, this point falls with the iron-rich line, a trajectory traced by cores rather than crusts. Like pressure trapped inside a dying star, its interior seems set to the phase of iron under relentless squeeze, a lattice packed as if spacetime were a vice. On its day side, metal would not merely exist, it would behave as landscape. The surface brightness hints at a skin that radiates like a low-albedo foundry, dark and incandescent. The wind, if any, would be rock vapor, a thin breath of sodium and iron atoms torn up at noon and driven toward night, where they might condense and fall like metallic frost. The star's magnetized plasma would shear across that exosphere, sculpting it into tails and fans that never quite become an atmosphere. Everything about this world suggests exposure, as if the planet had been stripped to its engine. The mechanics forcing that exposure are ruthless. Close orbits demand that energy be shed, angular momentum traded for heat, and any loose layer surrendered to the stellar field. Under such conditions, a planet's outer rock behaves like foam on a tide, carried away grain by grain, element by element, until the denser fractions remain. What endures near this star is what can endure. Iron and nickel under megabar pressures, crystal structures that shift between packed states without yielding, like a ripple frozen in spacetime. The planet's gravity announces that endurance with every completed orbit. The light curve carries secondary hints. The phase of maximum brightness arrives slightly before eclipse, implying a hotspot swept toward the evening side by supersonic winds, a thermal map without room for clouds. The nightside signature is faint, a dark hemisphere that returns little. The albedo is low. It is not reflective like ice or bright silicate dust. It absorbs, reprocesses, and emits with the quiet efficiency of molten surface and cooling metal plates. Each piece favors the same picture, a body paired to its core, skimming its star at blistering temperatures, iron made planetary. If confirmed to be what the gravity implies, this world rewrites the structure of the cosmos at the scale of close-in planets. It asks whether mantles are fragile near a star, whether high-energy impacts can peel a planet like an orange, whether centuries of irradiation can vaporize rock by preference and leave metal behind. It asks whether chemistry in the natal disk could bias solids toward iron in the inner furnace of a forming system. It shifts the starting conditions of planetary architecture from crust downward to core upward, and it does so with a single point that refuses to lie. The cadence continues. Transit after transit, the orbit holds. The starlight slips and recovers with disciplined precision, and the reflex motion remains too large for a mere rock. The planet's radius, derived from the depth of that shadow, stays too small for any world padded by gas. No hydrogen sheath. No helium bloom. Even a thin envelope would lift the curve above the measured value. Instead, the data prefer compression, the signature of metal phases packed under the weight of their own electrons. What the star's gravity counts is mass. What our telescopes gauge is size. Their ratio tells the rest. If the planet is a core laid bare, its magnetic behavior will differ. Its coupling to the star will imprint in subtle flares and radio whispers, and its surface will cycle metal and rock vapor across a horizon locked to the tide. There will be scars the size of continents where solidification races molten return, fracture lines that migrate with the substellar point like a strobe moving over an anvil. There will be seismic languages written into the way heat escapes, not through continents and oceans, but through plates of alloy and glassy crust that shatter and weld in a planetary foundry. The consequences for interior physics are exacting, because a world made mostly of iron leaves less room for uncertainty in the equation of state. The core is no longer hypothesis inside a mantle. The core is the world. For more content, like the video, subscribe, and tell me where you're watching from. The clockwork continues to mark hours, the shadow remains narrow, and the gravity remains heavy. The inference keeps circling the same conclusion, while leaving a gap no assumption can bridge without evidence we have not yet drawn from the light. The planet declares density. The star confirms mass. The radius refuses to grow. The narrative is coherent and yet unfinished, like gravity remembering its past but not revealing its cause. The orbit offers a clean line. The material beneath that line is harder to name. The data point stands in the metal-rich regime, but the registry of origins is blank. The equation was incomplete. A spectrum arrives with the wrong kind of emptiness. No broad hydrogen shoulders. No helium haze. The optical slope is flat where a thin gas envelope would usually scatter. The infrared window carries only the polished glow of a heated surface, and the eclipse contrast lands in a range that argues for compactness over puffiness. The light, stripped of ornaments, points at a body that keeps its radius small under ferocious heat. To understand that posture, pure metal must be defined without myth. Pure, in this context, is not the laboratory dream of perfect iron. It is a planetary core fraction swollen far beyond the habit of ordinary rocks. It means a body in which iron and nickel dominate the mass, where silicate minerals, if present, are reduced to a sheath so thin it functions like varnish rather than shell. Imagine calling a mountain a single mineral because it is mostly granite. The statement is true in bulk and false in detail. A near-metal world is granite by analogy, but the granite is an iron alloy, and the feldspar has been traded for trace silicates locked into high-pressure phases. The evidence for that bulk identity comes from density that outruns the ceiling permitted by silicate mantles. Take the measured mass from the star's reflex and divide by the volume implied by the transit, and the quotient pushes into a regime where only metal-rich models can stand. In words rather than symbols, the density lands near or above 7.5 grams per cubic centimeter and can climb toward 9. Range no plausible mixture of olivine, pyroxene, and basalt can supply under planetary gravity without a significant metallic contribution. The mass, radius point sits below the rock line and near the iron track, a quiet but emphatic verdict written by geometry and weight. Metal alone is not the entire story, because phase governs how that metal packs. Inside a world like this, pressure rises to many megabars, where iron assumes structures that squeeze without obvious sympathy. Hexagonal close-packed lattices compete with body-centered cubic frameworks. In each, the atoms arrange like marbles pressed by an unseen hand until orbitals overlap, the lattice constants contract, and the same count of particles occupies a smaller cage. At several thousands of kelvins, those lattices can melt, but under extreme pressure the liquid remains as dense as, or denser than, cooler phases. Thermal expansion tries to lift the radius, compression wins. The world stays small because its atoms do not grant space lightly. The surface conditions align with that interior logic. Close to the star, dayside temperatures can exceed 2000 kelvins by wide margins. At such heat, common silicate minerals move into a regime better described as a magma ocean with a rock vapor coma than as an atmosphere. If a silicate mantle survived, its outermost skin would be a melt deck, and the overhead gas would be a thin mix of metal and rock species with scale heights measured in handfuls of kilometers at most. That gas does not inflate the world. It drapes it, like a hot plume hugging a furnace floor. Any retained hydrogen or helium would behave differently, expanding the radius like a balloon inflating unevenly. The transit curve denies that expansion. Pure metal also implies a magnetic temperament. A large iron-nickel volume, moving in convective shells, can generate a dynamo with field strengths that couple tightly to the stellar wind. That field can carve the planet's exosphere into cometary geometries, produce radio emission in bands the star should not carry alone, and seed subtle temporal structure in phase curves as charged particles ride field lines into the night side. A silicate planet with a small core can do some of this. A near-metal world makes it the main act. The magnetism is not decorative. It governs escape, deposition, and the choreography of vapor returning to the dark hemisphere where it condenses as metal frost. Mercury offers a solar system analogy scaled to a gentler furnace. That small world contains roughly 7/10 of its mass in its core, an outlier forged by processes still debated. The worlds on this survey's shortlist push beyond that fraction, toward core shares edging between 7/10 and 9/10, a composition that alters every planetary property from moment of inertia to surface gravity. The comparison is not casual. If density and radius place this exoplanet family closer to iron than to rock, then their internal pressure profiles, melting curves, and electrical conductivities align with a metallic planet's blueprint rather than a stony world's script. The absence of a detectable gas envelope is not mere silence. It is an active constraint. Even a whisper of hydrogen or helium, wrapped around a hot planet, would stretch the limb, deepening the transit at short wavelengths and betraying itself in spectral lines that ride above the star's photosphere. Instruments tuned for such vapor find instead a surface-dominated signal. Eclipse depths that track black body-like emission from a tight radius, phase offsets that map winds over molten plains rather than cloud decks, a reflectivity so low it reads like cooled slag. If any gas exists, it is heavy, close to the ground, and constantly recycled by a day-night distillation. Iron, sodium, calcium, and magnesium atomized at noon, driven by pressure gradients at supersonic speeds, and rain back on the cold face as frost that melts on the next dawn. This is a planetary refinery, not a puffing world. At high pressure, iron does not behave as a simple constant density metal. Light elements can dissolve into the melt, sulfur, carbon, silicon, altering density, viscosity, and electrical conductivity. Each impurity carries its own equation of state, and even small admixtures can shift the core's compressibility. The mass radius point tolerates some dilution without departing the metal-rich curve, but those impurities matter for dynamics. They set the vigor of convection, the thickness of any stagnant layers, the ease with which crystallization seeds and grows. A near-metal world may still harbor a stratified core, with light element layers that behave like oil trapped beneath water, storing buoyancy that can be released in episodes. That storage changes how heat escapes, and heat flow shapes the strength and topology of the magnetic field. The phrase near metal invites a deeper mineralogical question at the boundary where core meets whatever mantle remains. Silicates under extreme pressure transform into phases with packed structures as unforgiving as metals. Bridgmanite into postperovskite, then into even denser frameworks predicted for pressures beyond Earth-like ranges. If a thin mantle persists, it will be chemically fractionated by the day-night vapor loop, mined of the more volatile components and left with refractory residues. Over time, the crust becomes a patchwork of quenched glass and exsolved metal beads, a surface where reflectivity cannot be predicted by simple albedo arguments. Observers read this complexity as a phase-dependent brightness pattern that refuses to match a single uniform model. Call the planet pure metal, and a practical consequence follows. The world's compressibility is lower than a rock's, so tides raised by the star deform it less for the same forcing. That smaller tidal bulge feeds back into internal heating and orbital evolution. Less tidal heat means different pathways for melt generation, different viscosity profiles for any residual mantle, different lifetimes for the magnetic engine. The feedbacks braid into a distinctive clock for structural evolution, one that can be read if the orbit's minute changes are tracked over many years with radial-velocity precision at the edge of what instruments can currently resolve. The phrase also carries a paradox. Iron's high thermal conductivity should move heat efficiently, flattening temperature gradients in the deep interior and calming convection. Yet a vigorous dynamo often requires strong gradients to drive motion. A near-metal planet asks both to be true: a core so conductive it smooths heat, and a convective engine so strong it sustains a field under blistering dayside conditions. The balance may depend on impurities, on crystallization fronts releasing latent heat, on light element snow falling inward like heavy ash. Data from light curves and phase spectra can weigh these possibilities indirectly, but the inference remains tangled. The spectrum still carries its silence where hydrogen would sing, the radius still refuses to inflate, and the density still leans toward iron even after every allowable error bar is pushed. The phrase pure metal survives the physics and the semantics, yet one discord persists. The measured emissivity in certain infrared bands hints at surfaces that are darker than molten silicate yet brighter than bare iron, a contradiction that alloy chemistry and roughness can mitigate but not fully resolve. The planet behaves like metal in mass and size, like slag in reflectivity, and like glass in its phase curve sheen. Something deeper is shaping the data. A secondary eclipse cuts the infrared channel like a clean switch. For a few measured minutes, the planet's dayside glow disappears behind the star, and the spectrum loses a slab of heat. That missing light is a ruler. From its depth, a brightness temperature is inferred, and from its color, a surface character is sketched. The eclipse returns, the glow reappears, and the orbit keeps time. Photons become coordinates. Transit photometry supplies the first geometry. A stellar disk dims by a small, repeatable fraction when the world crosses, and the exact curvature of ingress and egress writes a profile of how the planet's chord grazes the star. Limb darkening must be modeled with care, because stars are not uniform bulbs. Their edges are cooler, their centers brighter, and the transit silhouette passes through both. With high cadence and low noise, the light curve encodes the impact parameter, the inclination, and the planet-to-star radius ratio with a precision that tightens like a vise as more transits accumulate. Stellar granulation and instrumental drift tug at the curve like currents under a boat. Detrending algorithms learn their tempo and subtract them away without sanding off the signal. A radius only has meaning when the star's size is known. That number comes from spectra and parallax combined, a pairing as old as astrophysics and as modern as spaceborne interferometry. The star's effective temperature, surface gravity, and metal content sharpen its place on evolutionary tracks, and the parallax turns apparent brightness into absolute luminosity. Radius follows from these, not guessed but anchored, allowing the fractional transit depth to become an absolute planetary size. Every assumption is counted and carried into the uncertainties, because geometry respects honesty. Mass arrives from a different language, the back and forth that a planet's gravity imprints on the star's spectrum. Each orbit pulls the stellar lines first redward, then blueward, a measured dance that yields the planet's pull projected along our sight line. Activity on the stellar surface can masquerade as motion, spots rotating in and out of view, plages decorating the chromosphere. So the spectral time series is watched in multiple indicators at once. When the reflex matches the transit period, when phase and amplitude cohere across lines sensitive and insensitive to magnetism, the case gains weight. The semi-amplitude and the known geometry of inclination drain the last ambiguity. In that moment, a mass is not guessed. It is weighed like a hidden anvil by the sway it induces in its tether. Combine mass with radius and bulk density emerges. This is not a single value but a posterior landscape, a probability field over compositions. Interior models read it the way a seismologist reads echoes, mapping what combinations of iron, nickel, silicate, and void can fit inside those bounds while maintaining structural stability against self-gravity at the measured temperatures. The equation of state for iron at many megabars sets the stiffness of the core. The compressibility of silicates under the same squeeze defines the mantle's give. For planets this compact, only solutions heavy in metal keep the radius from inflating like a balloon forced around a stone. Phase curves add motion to the map. Over one orbit, the system's total brightness waxes and wanes as the planet's illuminated hemisphere rotates into and out of view. The shape of that wave tells how heat is moved. A peak before eclipse signals winds carrying the hotspot downwind. A peak at eclipse suggests a near-stagnant photosphere pinned by radiative timescales shorter than advection. The night side's faint glow reveals whether energy crosses the terminator as a jet or as a broad, sluggish tide. In worlds that skim their stars, the phase curve often refuses a simple sinusoid, hinting at patchy reflectivity, molten basins ringed by quenched crust, and jets that break and rejoin like braided rivers. High-resolution spectroscopy during transit peels off a different layer. The planet's limb cuts through the stellar continuum, and any absorbing species near the terminator stamp narrow lines that ride at the planet's orbital velocity. Cross-correlation with masks for sodium, calcium, iron, and other refractory elements tests for a rock vapor exosphere. Detecting such lines would be like seeing dust in a beam of sunlight. Their absence at the attained sensitivity limits the column density of those atoms and pushes the composition toward a surface-dominated signal. If lines appear but shift in phase relative to the planet's motion, star-planet interactions or magnetically guided escape may be redirecting the flow, a clue written in Doppler grammar. Transit timing variations check the mass from another axis. When neighboring planets tug on the transiting world, its clock drifts by seconds to minutes over months to years, a slow beat against the star's metronome. Fitting those drifts with dynamical models yields masses without relying on stellar activity corrections. Agreement between timing and radial velocity masses is a hard test. Disagreement is an accusation. Either unseen perturbers are in play, or systematic errors still stalk the data. In the handful of ultra-short period systems where timing is measurable, the compact planet often marches alone, leaving radial velocity as the primary scale, but the door remains open for faint neighbors hiding just beyond detectability. Thermal emission measured across multiple infrared bands sorts the surface into materials by their emissivities. Molten silicate has one texture, liquid metal another, quenched glass a third. By comparing eclipse depths at different wavelengths, one can infer whether the dayside radiates like a black surface or like a patched mosaic of bright crust and dark melt. If the brightness temperature in shorter bands exceeds that in longer bands beyond what a smooth spectrum would predict, the surface is not uniform. It is a landscape of hot lakes and cooler shelves. If the opposite holds, the surface may carry a glaze that reflects some wavelengths and swallows others, a signature of chemistry at work under brutal heat. Brightness maps reconstructed from phase curves sketch continents without calling them continents. They show a crescent of peak emission offset from the substellar point by tens of degrees, a swath of dullness along the antistellar meridian, and sometimes a second, smaller maximum that refuses simple circulation models. These features move little from orbit to orbit, a sign that the forcing is steady and the response is viscously pinned. Yet on seasonal timescales scaled to stellar activity cycles, the baseline can drift, as if the uppermost layers thicken and thin in response to flaring episodes that anneal the surface like a kiln turned up and down by a distant hand. Polarimetry at optical wavelengths contributes one more thread, measuring the tiny fraction of starlight scattered by the planet's dayside into a polarized signal. A low amplitude with weak phase dependence fits a dark, rough surface with little aerosol. A higher amplitude would argue for reflective condensates, but these orbits are too hot for most clouds, pushing the interpretation toward bright solid phases or particulate plumes lofted by impact vaporization at the substellar point. The measured polarization sits near the floor, reinforcing the picture of a low albedo skin. Yet small seasonal rises hint that new reflective patches can briefly form and vanish, unsteady and local. All of these observables add constraints, and the joint solution tightens. A radius measured in light, a mass measured in motion, a brightness measured in eclipse, a circulation mapped in phase. Each slice narrows the allowed interiors until only metal-rich configurations survive with headroom to spare. Yet a stubborn inconsistency remains in the multiband eclipse depths. In one atmospheric window, the planet is brighter than any plausible metal or silicate would be at the inferred temperature, and in a neighboring window it is dimmer than even a black surface should allow given the same energy budget. No known mixture of emissivities fits both bands without invoking texture at scales the phase curve cannot resolve or processes the simple radiative models do not include. The light insists on two incompatible surfaces occupying the same hemisphere at the same time. The mechanism is missing. A light curve folds cleanly on itself every not quite 8 hours, its trough narrow, its shoulders smooth, the star's brightness returning with mechanical regularity. The catalog tag is terse, the host a quiet red dwarf, and the reflex motion written into the star's spectral lines marches in phase with the transit clock. The calculated density presses beyond what a silicate planet can carry. The system commonly called GJ367 with Planet B becomes a template. A compact world skimming its star, its mass measured by the red and blue swing of stellar lines, its radius tied to the stenciled shape of the transit, its position in mass, radius space sitting where metal-rich interiors live. Thermal measurements during secondary eclipse add a dayside brightness consistent with a bare or thinly veneered surface. Nothing like the inflated limb a gas envelope would demand. The inference is not a flourish. It is the only configuration that keeps the planet as small as the light curve allows while staying as heavy as the reflex requires. Another star, warmer and brighter, submits a different set of numbers written again in words of light. The candidate long labeled K2-229 with planet B circles in days measured as a fraction of 1, and its density aligns with a heavy core fraction reminiscent of the innermost planet of the solar system, but carried to harsher proximity. Spectroscopy of the star suggests a typical abundance pattern, not a metal feast that would preordain iron worlds. The planet's mass from radial velocities, after correcting for the star's activity indicators, sits high for its measured size. The combination echoes Mercury, yet without the shared origin story. Phase curve hints show a low reflectivity and modest heat redistribution, as if a hot surface faces space with no significant aerosol layer to complicate the thermal language. If the star's composition is not anomalous, the planet's composition must come from process rather than from recipe, and the process must act with precision close to the star. A different puzzle emerges where two planets share the same sky. The system catalogued as Kepler-107 contains a pair near resonant spacing, one slightly inside the other. The outer member labeled C weighs more than the inner labeled B while sharing a similar size, a pairing that swings their bulk densities apart. The star bathes both in comparable irradiation, removing the easy explanation that one baked off an atmosphere while the other did not. In their mass-radius coordinates, the outer world nudges toward iron richness, while the inner matches a more ordinary rock. The contrast stands like a fault line in the same protoplanetary story. If spectra and stellar parameters are secure, then an asymmetric event must lie between these orbits, something that could peel the mantle from one world and leave the neighbor largely intact. The catalog does not tell that tale directly. It only draws a boundary between siblings that should have grown alike. A brighter, older star tagged with an HD designation offers another compact world that resists easy classification. The planet long referred to as HD 137,496 with planet B is subterrestrial in size, yet weighs heavily enough to lean into the metal-rich regime. Its radial velocity curve is clean, its transit shape sharp, and its inferred dayside temperature well into the regime where silicates do not merely soften but pool. Eclipse depths across multiple infrared bands suggest emissivities that fit a dark, patchy surface, while optical reflectivity remains stubbornly low. The star's slight evolution off the main sequence adjusts the parallax-derived radius and luminosity, but within the uncertainties the planet's compactness persists. Any hydrogen or helium clinging to such a hot, small world would register. None is seen. The data steer composition away from gas and toward alloy. Across the catalog of ultra-short period planets, the same geometry repeats with variations. Orbits compress into hours. Transits carve shallow, frequent shadows. Reflex motions march in time with the light curve. Densities stack beyond silicate ceilings. Some systems show phase offsets that betray sluggish winds unable to move heat far from the substellar point. Others display small pre-eclipse peaks consistent with a hotspot dragged to the evening side by a jet that remains thin and close to the ground. High-resolution transit spectroscopy occasionally picks up narrow lines from sodium or calcium where a rock vapor tail kisses the limb. But the detections are sparse, often near the threshold of certainty, and frequently contested by stellar activity that can mimic planetary signals. Where lines are secure, their Doppler shift rides with the planet's orbital speed, then veers, as if magnetic guidance or interaction with the stellar wind is redirecting the escaping atoms into a bent stream. The uncertainties that haunt each case are not decorations. They are part of the structure. Stellar radii depend on effective temperature and parallax. Errors in either propagate directly into planetary size. Radial velocities ride on line profiles that can be skewed by star spots and faculae. Activity cycles can align with planetary periods and counterfeit mass. Detrending a light curve without erasing a shallow transit asks for a balance between removing noise and preserving a signal only a few parts in 10,000 deep. Yet in the aggregate, these hazards do not erase the pattern. The planets that hug their stars most closely carry densities that press toward metal. The mass, radius points lie where iron tracks cut across the diagram like a seam in a forged ingot. Each suspect world adds a different diagnostic. The red dwarf system offers a clean geometry and a small radius that maintains its compactness across instrument pipelines. The Mercury analog skates near a period where tidal forces are merciless, inviting pathways that peel silicate layers while leaving metal behind. The resonant pair with mismatched densities refuses explanations that depend only on irradiation or stellar composition, signaling a violent asymmetry in their histories. The bright subgiant host delivers higher signal-to-noise, enabling multiband eclipse photometry that hints at emissivity contrasts across the dayside. Together they contour a family of planets for which metal is not a buried center, but the bulk of the body. The dynamical context complicates the picture. Transit timing variations, where measurable, are small, implying sparse companionship in the closest orbits, yet radial velocity residuals sometimes whisper of outer companions that never cross the stellar disk. Tidal decay rates inferred from tiny changes in transit times over many years hint that some of these worlds are slowly spiraling inward on astronomical timescales, tightening the leash and intensifying escape. In a few systems, star-planet interaction indicators brighten at specific orbital phases, as if magnetic stresses were depositing energy along fixed footpoints on the stellar surface. Those brightenings correlate with shifts in the apparent planetary lines, suggesting that material lifted from the planet is being swept into arcs guided by a field shared between star and world. As the list of suspects grows, the statistics begin to harden. Ultra-short-period planets appear more frequently around stars with higher overall metallicity, a trend that can be read two ways. Metal-rich disks build more solids everywhere, making it easier to grow massive cores that can later be stripped. Or chemistry near the star favors iron-rich condensates when oxygen is scarce, biasing the earliest building blocks toward metal before stripping even begins. The two readings produce similar mass, radius outcomes, but predict different correlations with stellar abundances of refractory elements. Current spectroscopic surveys are precise but not decisive. The scatter in stellar compositions leaves room for both pathways. The catalog's narrative gains weight with every measured orbit, and yet acquires friction where individual systems break pattern. One compact world shows an optical brightness too high for a dark, molten dayside, as if patches of reflective solid persist at temperatures where theory expects liquid. Another displays an infrared slope consistent with glassy rock rather than metal, while its mass, radius point still requires an iron-heavy interior. A third carries a phase curve shape implying efficient nightside cooling, at odds with the low scale height expected for heavy vapor. The family resemblance is strong, but not exact. The anomalies are not noise, they are features. The worlds look metal by weight and rock by light, and the same mechanisms that forge their densities do not fully explain their faces. The laws of physics have begun to divide against themselves. A burst of lines appears where the star's spectrum should be smooth, faint notches from neutral sodium and neutral iron slipping in and out of phase with the planet's motion. The features sharpen after a stellar flare and then relax, as if a plume had been heated and stretched. The velocities match the planet near transit, then skew, bending as though guided. The signal does not belong to a gas giant's swollen limb. It belongs to an escape stream clipped tight to a compact world. The physics points to a forge with more than one hammer. A giant impact is the first and loudest strike. Two protoplanets cross orbits, one heavier in metal, one richer in silicate. The collision imparts energy far above the binding of a thin mantle, driving rock into orbit as vapor and melt while the denser core survives as a single remnant. Observables would follow. Infrared clocks tick faster for years to decades as hot debris cools. A bright excess of warm dust can hang close to the star like ash caught in a slow convection cell. Transit shapes acquire shallow, time-variable skirts as small grains drift across the core ahead of and behind the planet. The planet's spin axis tilts, and the orbit may misalign with the star's equator, readable through the way stellar lines wobble during transit when the planet hides one rotating limb more than the other. The remnant's mass, radius point leaps downward toward the metal track while the neighboring worlds remain ordinary, a contrast cut into the catalog like a scar. The signature is violent and asymmetric, and it explains abrupt iron enrichment without asking the star to share that trait. Selective evaporation is a quieter but patient second hammer. Irradiation on ultra-short orbits drives the surface into a magma state and lifts molecules into a rock vapor sheath. Lighter silicate species depart more readily, while iron and nickel condense at higher temperatures and fall back. The planet becomes a distillation column locked to a tide. Vapor rising at noon, winds pushing the plume, condensates snowing out on the night, recycled material carried into dawn. Spectra test this behavior directly. Neutral sodium and neutral potassium lines bite into the stellar continuum just before and after transit, deeper on days following flares, then fade as the plume cools. The absence of hydrogen and helium signatures confirms that any primordial envelope is gone. The remaining gas is heavy and close to the ground. Over millions to billions of years, the column removes rock and leaves alloy, like building a skyscraper in the Stone Age by lifting one stone at a time, with gravity, heat, and chemistry acting as the pulleys. Roche geometry applies a third hammer when the world drifts close enough for gravity to stretch it beyond self-control. The planet's figure elongates along the star-planet line, and at the inner Lagrange point a saddle opens where material can spill. Light curves capture the deformation as ellipsoidal variations, tiny brightening and dimming synchronized to halves of the orbit, the star's light reflected by a shape no longer spherical. If overflow begins, the transit can become asymmetric. Ingress steeper than egress or the reverse, depending on whether a stream leads or trails. High-resolution spectra find absorption at velocities that do not match winds alone, as if the stream is constrained by the shared gravitational potential. Over time, the orbit can shrink as mass is transferred, and the period drifts by milliseconds across many years, a secular trend carved into transit timings. A measured decay rates the closeness of the approach and the strength of tides inside a planet whose compressibility is low because metal does not yield easily. Disk chemistry is a fourth hammer that strikes before the world even forms. In the inner nebula, where temperatures scorch and oxygen abundance can dip relative to metals, iron condenses early while many silicates remain in vapor. Grains born, there are iron beads with thin rock skins, accreting into embryos that carry high core fractions from birth. The test lives in the host star. If planets track stellar ratios of refractory elements, especially iron to silicon and magnesium to silicon, then the metal loading is primordial. If instead planets are iron-rich around stars whose photospheres are not, then the loading is evolutionary. Precision stellar spectroscopy reads those ratios to parts per hundred. The correlation is not yet clean, but early samples lean toward mixed origins, as if some worlds carry the disk in their bones while others were the memory of later violence. Tidal migration and heating form the backdrop that strengthens every other hammer. A planet born farther out can be driven inward by interactions with the disk or by gravitational kicks from companions. Eccentricity pumps and drains, tides damp the orbit, and energy deposited deep inside the world raises temperatures at the base of any mantle. A metal-rich planet shares its heat readily, so the thermal gradient that drives convection and volcanism becomes a contest between conduction and internal sources. Where rock remains, it fractures under stress and leaks into space as vapor. Where only alloy persists, viscosity increases and shape becomes resilient, resisting further deformation even as the star pulls harder. The migration can be read in the skyplane as misalignment between orbital plane and stellar spin, extracted from the transient twist of spectral lines during transit. Orbits aligned suggest gentle disk migration. Orbits skewed suggest violent pathways. The distribution across ultra-short periods shows both temperaments, which means both paths feed the furnace. Each hammer leaves different residues in the data. Giant impacts predict debris signatures, misalignments, and siblings with mismatched densities. Selective evaporation predicts heavy metal lines without hydrogen counterparts, phase curves showing a sharp hotspot and slow, age-dependent shrinkage toward higher density. Roche overflow predicts ellipsoidal modulation, asymmetric transits, and measurable orbital decay. Disk chemistry predicts correlations with stellar refractory ratios and systems where multiple close-in worlds share similar high densities without evidence of trauma. Tidal migration predicts a spread in spin, orbit angles, and a relationship between decay rates and internal dissipation that depends on structure. The catalog carries examples that satisfy parts of these predictions, but none that satisfy all at once. One compact planet exhibits a persistent sodium tail that waxes after flares yet orbits a star whose refractory abundances match solar ratios, arguing for ongoing escape without primordial bias. Another shows a clean ellipsoidal signal and period drift consistent with tidal decay, but its phase curve implies nightside cooling stronger than expected if a heavy exosphere blankets the surface. A third sits in a resonant chain with neighbors, yet alone carries a metal-rich density, a configuration that strains the idea of a solitary giant impact inside a tightly packed system without disturbing the chain. There is an energy bookkeeping issue that refuses easy closure. The mass loss inferred from metal lines, integrated over the age of the system, often falls short of the rock that would need to be removed to move a planet from a stony composition to a near-metal one. Giant impacts can bridge that deficit in an instant, but then the long-lived metal lines should fade as debris clears, while some worlds keep their plumes active over many seasons. Disk chemistry can start a world iron-heavy, but then siblings should share the trait, and in several systems they do not. Tidal decay can supply power, but the measured period drifts are sometimes too small to heat a mantle enough to vaporize silicates at the required rates. The fingerprints overlap without a single hand to match them. The spectra continue to catch neutral iron where only silicate vapor would be expected. The light curves continue to trace shapes that hint at overflow while periods barely change, and stellar abundances continue to scatter across values that neither demand nor forbid primordial iron excess. The forge is working, but the order of blows and the relative strength of each hammer remain unmeasured. The architecture of cause and effect looks complete until the numbers are placed, and then one relation breaks under the weight of another. The mechanism that reconciles the mismatched energy budgets, the persistent escape, the occasional debris, and the mixed stellar chemistry is missing. A narrow radio hiss rises at the same orbital phase on consecutive nights, drifting in frequency as the geometry changes by degrees. The star is quiet at these wavelengths. The modulation tracks the planet. If it is cyclotron emission, the tone sets a floor on magnetic field strength at heights where vapor thins into space. The signal does not linger. It flickers, as if parcels of charged gas were swept across field lines and accelerated near a bow shock. The planet, small in radius and heavy in mass, carries a magnetosphere scaled down to its compactness and yet broad enough to sculpt the escaping cloud. Magnetism enters the light curve as a silent hand. In thermal channels, the planet's day blazes and its night returns only a whisper of heat. The phase curve is asymmetric. Maximum brightness arrives before secondary eclipse by a handful of tens of degrees, a displacement that marks a hotspot carried into the evening by winds. Those winds cannot climb high. A heavy vapor has a low scale height, so the flow hugs the surface like a hot river under low ceiling. The derived advection timescale loses against radiative cooling. Energy is dumped back to space faster than air can move it around the limb. Nightside brightness remains dim, not because the planet is cold, but because the emitting layer collapses close to the ground where it is quickly quenched and darkened. Spectroscopy looks for atoms in that river. During transit, the stellar continuum is combed by templates for neutral sodium, neutral calcium, and neutral iron. Cross-correlation pulls out weak lines that ride with the planet's velocity, then veer near egress, as if the stream of escaping atoms were bent by magnetic draping. The line cores are narrow and the wings shallow, an imprint of temperatures consistent with vapor lifting from a magma surface rather than from a high-altitude corona. On nights following stellar flares, the lines deepen, then recede over a few orbits, a memory of impulsive heating written in optical depth. Hydrogen is invisible at the required sensitivity, not because it never existed, but because it cannot survive this furnace. What remains is rock distilled into gas and pulled sideward by pressure gradients. Surface emissivity reveals itself through the color of the eclipse depth. At longer infrared wavelengths, the planet radiates like a near-black slab. At shorter infrared wavelengths, the brightness slips below a simple thermal shape, as if patches of quenched glass or reflective metal plates shared the dayside with molten plains. The transition between these patches may be keyed to tidal geography. Directly under the star, melt ponds deepen and coalesce. Toward the limb, quenched crust thickens by degrees, then fractures as it drifts into heat again on the following orbit. The pattern is not smooth. Eclipse mapping produces a mosaic of bright and dark tiles, sharper than circulation alone would draw, implying a rheology that flips between fluid and brittle on scales of tens of kilometers. Metal and rock do not boil alike. Iron vaporizes at higher temperatures and condenses at higher temperatures than common silicates. So the plume composition shifts with local heat as the substellar point migrates westward across a surface that is tidally pinned. That migration is not the motion of the planet. It is the movement of heat through a lopsided atmosphere that never escapes the lower reaches. The result is a chemical front that follows the hotspot like a shadow. Sodium lines strengthen on the eastern limb, where silicates flash and escape. Iron lines brighten closer to the substellar point, where temperatures suppress silicate vapor and feed metal into the stream. Toward the night side, both species collapse out as frost, plating the surface in dark veneers that will melt at dawn and return to the circuit. The planet becomes a refinery locked to a clock. Polarization at optical wavelengths remains faint and stubborn. A low amplitude with weak phase structure aligns with a rough, dark surface that scatters little. Yet brief enhancements appear after meteor streams intersect the orbit, inferred from sporadic increases in stochastic noise and tiny, short-lived slivers in the transit ingress. Micrometeoroid impacts excavate bright plumes that loft particulates for minutes to hours before they sinter and fall. During those windows, polarization ticks upward and optical brightness climbs by a fraction. The effect defines the grain size and the refractive index of the dust, parameters that point towards silicate glass rather than metal flakes, consistent with a surface that segregates into rock-rich froth atop a heavier metallic substrate. The night side is not silent. Occultation spectroscopy of the dark hemisphere pulls a weak continuum shaped by a thin, cool layer that must be replenished every orbit. That replenishment can only come from day-to-night transport and from outgassing along fractures that open under thermal contraction. The fractures map into longitudinal bands where stress accumulates and releases, like tectonics without plates. Expansion at dusk, contraction at dawn, a breathing crust that never drifts far but never rests. When mapped against the phase curve, these bands correlate with small, periodic jitter in the brightness peak, a reminder that meteorology and geology are the same phenomenon under different pressures. Interior physics imposes discipline. A planet that is mostly iron should conduct heat efficiently, flattening deep temperature gradients. High conductivity fights convection, yet dynamo action requires motion. One pathway remains. Crystallization at the center releases light elements into the liquid outer core, building buoyant plumes that carry charge and sustain a field. The rate of that release depends on the mixture dissolved in the melt: sulfur, silicon, carbon, each changing density and viscosity. Electrical conductivity at these pressures is high, so ohmic diffusion is slow, favoring long-lived field structures. If the radiohist truly marks cyclotron emission near a magnetopause, the field magnitude at altitude matches a convecting core of significant vigor. The rotation rate is pinned by the tide, so the engine must be powered more by composition and latent heat than by shear. Star-planet coupling complicates the picture. Chromospheric indicators in the star brighten at specific orbital phases that recur for months, as if magnetic footpoints were fixed where the planet's field reconnects with the stellar wind. During those phases, the metal lines in transmission skew, their centroids pulled blueward or redward beyond the ballistic wind expectation, as if charged atoms were entrained along field-aligned paths. A small excess in ultraviolet flux coincides with these alignments, consistent with precipitation onto the dayside upper layers. The coupling deposits energy in patches, promoting local escape that is not symmetric around the substellar point. Phase-resolved spectra record the imbalance as a lopsided exosphere. Ellipsoidal variations in the out-of-transit light provide a second handle on shape. The planet's bulk is slightly stretched by tides, an effect that modulates the star's light by a vanishingly small amount. The amplitude depends on rigidity. Metal resists deformation better than rock, so the signal is small, yet present. From it, one can infer a love number that encodes the interior's willingness to yield. The measured value sits near the expectation for a dense core with a thin, hot veneer. Combined with the period's near constancy across years, these data say the body is stiff and the orbit is not shedding energy rapidly. The field exists without help from tidal heating large enough to upset the phase curve. There is a heat budget that refuses to balance. Eclipse depths insist on a dayside temperature higher than a uniform black surface would reach at the measured albedo and stellar flux. The excess could come from dissipation in the upper layers where the star's magnetic field drags against the planets. Yet the radio signal suggests a magnetosphere that should shield those layers efficiently. If dissipation occurs deeper, the high conductivity of an iron crust should spread it laterally and smear out hotspots, yet the phase curve keeps the emission peak sharp and displaced toward evening. The brightness maps ask for localized energy injection. The magnetospheric geometry argues against it. The surface acts as if it can be both a near-perfect conductor and a patchwork radiator at the same time. The mechanism that lets a metal world host stationary thermal islands under a field that should erase them remains unmeasured. An X-ray pattern flashes across a detector as a laser-heated anvil cell drives iron past many megabars. Bragg peaks slip, merge, and reappear at new angles. The lattice abandons one packing and accepts another. The shift is small in the lab and immense in a planet. Each increment in compressibility moves a world's radius by kilometers and its core by fractions of the whole. The equation of state is not a table, it is a lever. Mass, radius posteriors for compact planets tilt when those peaks move, and interior models that once tolerated silicate ballast now require iron purity higher by measurable degrees. A single line in a diffraction image reshapes the density that light curves must support. Conductivity measurements follow. A pulse of current races through molten iron infused with sulfur or silicon, and the response time shortens as pressure climbs. High conductivity flattens deep temperature gradients, making convection harder to maintain while making magnetic diffusion slower to erase. Dynamo thresholds are recalculated. The field inferred from cyclotron radio hints becomes a diagnostic of light element doping, not just of core size. A stronger field with a stiff interior implies buoyancy fed by composition rather than by shear, a pattern that feeds directly into the exosphere's geometry and the phase curve offset. Laboratory seconds translate into astronomical decades because the numbers decide how heat moves where telescopes cannot look. Spectral line lists at high temperature refine the search space. Cross-sections for neutral iron and neutral sodium updated for thousands of kelvins, and high collision rates change the depth the model predicts during transit by a measurable fraction. Retrieval frameworks recalibrate, and upper limits on metal columns tighten by orders spelled out in words, not symbols. Where a detection existed at the edge of noise, it either stabilizes or vanishes. A real line rides the planet's velocity through ingress and egress, and bends where magnetism bends the flow. A spurious line follows stellar activity indices instead. The difference decides whether escape is heavy and surface-borne or light and primordial, and that decision locks or releases entire formation pathways. Demographics add weight. A histogram of ultra-short periods grows in height with stellar metal content, but the increase is not uniform across spectral type. Cool stars carry more of these worlds than hot stars at the same bulk metallicity, an asymmetry that cannot be blamed on detection bias alone. Close-in lifetimes against photoablation stretch around quiet red dwarfs and shorten near active blue-white hosts, leaving a sculpted valley where silicate mantles cannot survive, but metal cores can persist. The catalog becomes a map of survivorship, and survivorship is a constraint. If cores are all that remain in some orbits, then the rate at which mantles are removed can be read from the mass distribution slope, and that slope calibrates the energy budget that earlier parts of the story keep failing to balance. Timing resolves slow mechanics. Transit centers drift by seconds across years, and that drift fixes tidal dissipation inside the planet with a precision that spectrographs alone cannot reach. A stiff world of iron yields less and decays inward more slowly. A world with a residual hot mantle yields more and drops faster. Folding thousands of orbits reduces phase noise until the curve reveals whether the period is constant within measurement or bleeding energy into heat at a rate consistent with the brightness temperature. When decay is absent yet the dayside runs hot, extra power must be entering elsewhere. The discrepancy refuses to be a footnote because the phase curve's peak has a location and a width that leave little room for unseen sources. High-resolution spectrographs on stable optical benches measure stellar reflex motions down to dozens of centimeters per second spelled in words. Those impulses, averaged across seasons, carve away the last systematic excuses. Residuals that remain at the planet's period without correlating with chromospheric tracers are gravity, not spots. Mass becomes a clean number. Add the radius from a light curve that has been corrected with a limb-darkening law anchored by stellar interferometry, and density gains the rigidity of a truss. Interior solutions narrow until the remaining variance is governed by the lab's iron lever and the telescope's phase map, not by calibration drift. Infrared imagers trace the rest. Multiband eclipse depths define emissivity spectra that discriminate between molten silicate, quenched glass, and metallic pools under ash-colored crust. Dayside mosaics inferred from phase curve inversions sharpen into thermal isotherms that obey winds until they do not. Where winds fail, something local injects energy or resists loss. The pattern repeats on multiple worlds with similar periods and different stars, so the cause is planetary, not stellar. Magneto-atmospheric coupling is a candidate. So is latent heat release from crystallizing alloy near the surface, a strange regime where metal plates out of a melt at pressures high enough to stiffen it while temperatures near the surface are still above the liquefaction point for rock. Each candidate carries distinct timing and spectral signatures. None yet locked to the data without scraping against another constraint. Formation histories separate under this scrutiny. A giant impact leaves a misaligned spin, orbit angle. A debris glow at mid-infrared wavelengths that decays on timescales measured in years to decades, and siblings whose densities diverge within the same system. Selective evaporation leaves aligned orbits and age-dependent shrinkage toward higher density with metal lines that wax after flares. Roche overflow leaves ellipsoidal variation, asymmetric transit ingress, and measurable decay. Primordial chemistry leaves correlations between planetary compactness and stellar refractory ratios that persist across multiple planets in one system. The catalog contains worlds that match pieces of each script. The problem is not a lack of pathways. It is the presence of more than one in the same sky. Planetary fate becomes a physics program rather than a story. How a near-metal world cools sets the life expectancy of its field, the shape of its exosphere, and the rate at which metal snow returns to melt. Cooling depends on conductivity and on the availability of light elements to build buoyant plumes. Those elements are diagnosed by the speed of dynamo drift and by the way radio emission cuts across the orbit when the magnetopause breathes against the stellar wind. The distance between these observables and first principles narrows until the remaining gap is small enough to be a property rather than an ignorance. Inside that gap lies the structure of cores, the melting behavior of alloys under gravity, and the rheology of magma under constant irradiation. Each is an input for planets not yet found and a boundary condition for those already counted. The big scale responds. Population models that couple disk chemistry with migration and escape recreate the abundance of ultra-short period planets only when the inner disk contains zones where iron condenses early and silicate condensation lags by distances measured in tenths of astronomical units. In those models, a minor change in oxygen relative to metal shifts the place where rock can exist, reshaping the inventory of cores for an entire class of stars. That prediction can be checked by measuring refractory ratios in stars across temperature and age, while tallying the radii and masses of their closest planets. The result will either align with the chemistry lever or push the community back toward impacts and tides as the dominant sculptors. Either outcome injects precision into stories that were once qualitative. Guidance for observations becomes terse and direct. Obtain phase curves in multiple infrared bands with cadence high enough to pin the hotspot shift and low enough noise to detect secondary features. Target transmission windows where heavy metal lines sit cleanly between stellar features, and resolve them at velocities that separate planetary motion from stellar noise. Pursue radio searches at frequencies set by cyclotron conditions near plausible magnetopauses and phase bin the signal against orbits and flares. Track transits for years to measure drifts at the level of words rather than symbols. Anchor stellar radii with interferometry when possible and with parallax and spectral energy distributions when not. Each prescription pushes toward one parameter that decides between pathways instead of wandering across many that do not. One contradiction refuses to be moved by new instruments or better tables. The heat pattern across daysides demands stable thermal islands that resist both wind advection and conductive smoothing in a crust that should carry heat like a rail. The islands persist on worlds with different stars, different inferred impurities in the core, and different magnetic hints. No combination of emissivity patches and shallow circulation closes the gap without violating the measured love numbers or the radio-inferred field strengths. Either metal under these conditions enters an unmeasured phase that changes anisotropic conduction near the surface, or energy is arriving in a geometry that standard magnetohydrodynamics does not predict. The hinge where those two readings meet is missing.